All right, so we today are going to talk about objects that are moving in the vertical direction. So far we've looked at our kinematics equations only in the horizontal direction. Today we're going to change gears a little bit and look at falling objects, or objects that are accelerating in the vertical direction. Okay, so an object that is in free fall, we still consider to be in constant acceleration. Does anyone know what the constant acceleration might be in the vertical direction? If something's falling through the air, what is it that keeps it moving in the downward direction? Gravity. Okay? So a constant acceleration here is because of gravity. Okay, so I want you to think about this question here. Does a heavier object fall faster than a lighter object?
Yes.
Okay, you all say yes.
Yes.
Okay. No. The answer is no. Okay? And I'm going to show you why that is. Okay? Without air resistance, as long as two objects are the same shape and roughly the same size, they're going to fall at the exact same rate. Okay, do we see mass plugged into our kinematics equations anywhere? No. That means the mass of the object has nothing to do with the rate at which it's going to fall. It has more to do with the surface area and really the amount of air resistance that is kind of available here. Okay? But we're going to watch a little video that kind of shows us, talks about this discovery a little bit. Vertical direction. So we still consider gravity a form of acceleration. So you might see it as the little a for acceleration, or you might see it as a g, right? A little g. Okay? But essentially, this acceleration is due to is equal to 9.8 meters per second squared. And what direction is this acceleration always going to be going? Downward. So that means you should really include here negative 9.8 meters per second squared. Okay, because we're going to plug in that negative because it's always pulling us to the center of the Earth. Okay, that's where gravity is based, is at the Earth's core. Okay, so we always envision it as going downward, but realistically it's being pulled to the Earth's core, which is always in the down direction for us because we're on the Earth's surface. Okay, so we're going to always have gravity equal to negative 9.8 meters per second squared. Does this acceleration always get used for horizontal problems? No. Okay. Horizontal kinematics have varying accelerations, right? We calculated acceleration in all of our horizontal kinematics problems. In vertical kinematics, this is a variable that you just know. So anytime an object is moving vertically, its acceleration is always going to be negative 9.8 meters per second squared. Okay? Even if it's pushed down, that velocity, initial velocity, makes no difference to us in terms of the acceleration due to gravity. Same thing if an object gets thrown upward. Gravity is still pulling it back down. Okay, so no matter what the direction of our object is here, acceleration is always going to be negative 9.8 meters per second squared.
So if you throw something in the air...
Okay. So our objects that are considered to be in free fall, that's anything that's moving freely through the air. Okay, and right now we're going to look at objects that are specifically just going straight up and coming straight back down. Or they're just being dropped straight to the ground. We're not looking at anything that's moving through the air in both directions yet. Okay? So this means it has constant acceleration in the y direction, which happens to be the acceleration due to gravity. Right? Okay, so go ahead and get written down what you need to, and then we're going to work through this together. Okay, you'll need your calculator out, your equation sheet out. Your equations that you wrote down work the same for vertical problems. Okay, the only change is that you're looking at a constant acceleration, which is negative 9.8. Okay, so your kinematics equations remain the same. Alright, so here I'm going to draw a little diagram of what's happening in our motion. Here's our object on the cliff. It's being dropped, and it's going to land on the ground somewhere. Okay? Our tower is 70 meters tall. Okay? This is something that's really important for vertical problems, and I'll explain why I do this here in a second. But I always like to choose my origin where the motion begins from, right? Have we talked about that with our horizontal problems? I like to place my origin, or my starting point, where my motion begins from, which on this case happens to be at the top of the tower, right? Because we're on top of the tower, we're just dropping our object. Okay, so I like to place my origin or my starting point at the top of the tower as opposed to putting my origin at the ground. Okay, I like to make it where the motion begins. And the reason I like to do that is because it gives me a couple easy variables then. Okay, so let's think about what's happening here. Just keep that in mind as we continue to work through this, all right? It says that a ball is dropped from a tower 70 meters high. How far will it have fallen? So what variable does that mean we're going to solve for? Distance, right? And are we solving for initial distance or final distance? Final. So we're going to solve for distance final. That's going to be our question mark. Okay, what do we know about our initial distance?
70.
The tower is 70 meters tall, but do we really care how tall it is at this point? Because we want to find out how far it's fallen. The reason I put my origin at the beginning of my motion is so that my initial distance is 0. Okay, that's the whole reason I do that. Okay, if I didn't do that, our initial distance would have to be 70, and then my final displacement would come out kind of funky. Okay, right now we want to make our origin where our motion begins from. Okay, so right now the 70 doesn't have anything to do with our problem at this point. We really don't care about that 70 meters. Because do we think it's going to fall the whole height of the tower in 1 second?
No.
Probably not. Okay, probably not. So what else do we know in our problem? This particular question is asking us for 3 different answers. One after 1 second, after 2 seconds, and after 3 seconds. So what's the other variable that we know for our first problem? We know that time is equal to 1. Okay. We know a couple other things. What do we know about our acceleration?
It's
Negative 9.8. And what do we know about our initial velocity? Do we know it?
0.
It's 0. Why is it 0?
Because they haven't dropped it.
Okay, almost, but it's at the origin that kind of, okay, what I'm thinking is here, the instant that I let go of it, the instant that that comes out of my hand, it doesn't have velocity yet. It's not like I'm throwing the object and it's starting with a velocity. The instant that it comes out of my hand, it has no velocity. So we want to think about it the moment it becomes a freely falling object. And for that tiny instant, it has no velocity yet. Okay? So that means that initial velocity is 0. And that's purely because it is dropped. Okay? If it was thrown, if it was launched, if it was doing something else, it would not be 0. But when something is dropped, if something maybe just falls off the tower, blah, 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 that initial velocity is 0. We know our initial velocity, we know our acceleration, we know our time. Is there an equation that you see that we can use here to solve for time? The second kinematics, right? That looks like this. dF equals di plus vit plus 1/2 at squared, right? We can use this equation. So we don't know our distance final. Our distance initial is 0. Our initial velocity is 0. 1/2 negative 9.8 times 1 squared. Remember that only the time variable is being squared here, not the whole term. Okay? So that means distance final is equal to negative 4.9 meters. Right? Because I'm taking negative 9.8 times 1/2 times 1. Does everyone understand why these terms are both 0?
Because you'd be multiplying the second one by time.
Mm-hmm.
The initial distance is displacement.
Good, good. We want to make initial displacement 0 as often as we can, and the way that happens is to place our origin at the beginning of the motion. Okay, so you need to think about where your motion is starting from. Drawing the diagram will help. Then you place your origin there. So that's why I make this little cross of my axes here to tell myself where my origin is. Okay? Anything times 0 is 0, so even though our time is 1 here, we're going to take it times our initial velocity, which is 0. So that whole term is 0. Okay? So that means after 1 second, we've only fallen about this far. Does anyone understand why my displacement here is negative?
Because
It's sort of. Okay, I don't want you to think of... Okay, so after 2 seconds, the only thing that changed was the 2. That means after 3 seconds, so 3 squared, negative 44.1, I think. And what's our units here for displacement? Meters. Good. So that means after 3 seconds, we're way down here, 44.1. Okay, so if I had drawn this completely to scale, you would see an increase in the displacement with each second. So the interval between 0 and 1 seconds, it hasn't traveled very far. Between 1 and 2 seconds, it's traveled a little bit farther. Between 2 and 3 seconds, it's traveled a little bit farther. Can we see that increase in our intervals there a little bit? Yeah. Okay, so if you looked at that motion diagram, that would also show you that it is accelerating as it falls. Okay? Okay, so you have to be careful about this, whether your book really includes that negative when it should have it. Okay, very good. Time is equal to 2 seconds, and we're solving for final displacement. Okay, can we use the same equation here? Yes. We can, but we have one term that we cannot make 0 anymore, right? Because our initial velocity is no longer 0. So displacement final is equal to d sub I plus vi t plus 1/2 at squared. Okay. Distance final is what I'm solving for. Distance initial is still 0, but my initial velocity this time is not 0. So we're taking 3, negative 3 really, sorry, times 2 plus 1/2 negative 9.8 times 2 squared. So is this farther down the tower as opposed to when we just dropped it? Yes. Yes, it's traveled 25.6 meters below where it started. Okay, so if I were to ask you how high up the tower is the ball after 2 seconds, you would take 70 minus this answer, and it would tell me basically how high it is above the ground at that point. Okay, we don't usually turn questions around like that, but here it's fallen this height. Okay. Any questions about that? All right, let's go ahead and get written down this one, and then we're going to have to work through this one together because this takes it a little bit step further. Because acceleration and gravity is always pulling you down, okay? So it's still going to be negative. So let's think about here. Our diagram looks something like this. Here's my, Here's my little person, okay? Here's my object. It's going to go into the air. Okay, so it's going to go up into the air, and then it's going to fall back down, okay? It's going to go straight up and come straight back down. So person throws the ball upward with an initial velocity of 15 meters per second. That should be a big clue for us, right? That initial velocity is equal to... No, not 0, sorry. Why negative 15? No, positive 15. Right? Initially, he's throwing it upward. Okay, so we're thinking just about this first portion of the motion. So positive 15 meters per second. Okay, is there anything else that we know? Good. Initial displacement is equal to 0. Good, because my origin is right here, where the motion begins from. So it's at the height of his hand. It's not at the ground, it's at his hand, where the motion starts from. Okay, where that object becomes a free-falling object. Yes, okay, you know acceleration. That wasn't really a question, but okay. Yeah, I don't know. Okay, acceleration is equal to negative 9.8. And tell me what we're solving for here first.
How high velocity.
Final distance is what we're solving for, but we do know something about the final velocity at peak height. Okay? it's 0, right? When we throw an object into the air, at its very highest point, it stops for just a tiny portion of a second. Okay? It stops. So since for this first portion of our motion, we're only looking at how high it goes, we're only looking at the first half of this motion, right? From its hand to its peak height, which means final velocity here is 0. Okay? And this is at peak height. Okay, so at peak height. So this is only the first half of the motion. Are we all on the same page there?
Yeah.
Okay, this is at peak height, the final velocity is 0. So now, do we have an equation that we can use to solve for?
Yes.
Yeah, we can use the third kinematics equation. It looks like this. Vf squared equals Vi squared. That's 2a df minus di. Okay? So final velocity squared we know is 0. Okay, 0 squared equals 15 squared. We have okay, plus 2 times negative 9.8 times df minus 0. Okay, which realistically goes like this. 0 equals 225 plus negative 19.6 df. Okay, because df minus 0 is just distance final, right? You can drop that 0. So we multiply these all together. It's important here in this equation that you're being careful about multiplying 9.8 times 2, because the other equation is 1/2 times our acceleration. So sometimes people mix those up. Just be careful here when you're doing these calculations. When you're supposed to multiply by 2, multiply by 2. When you're supposed to multiply by half, multiply by half. Okay, just be careful because that gets mixed up a lot. Okay, algebraically here, what's my next step? I want to subtract over that 225. Subtract over 225, which gives me negative 225 equals negative 19.6 df. So what do I need to do here? Divide that over. Do not add that over. Divide by negative 19.6. Divide by negative 19.6. And that gets my final displacement equal to? What is it? Yeah, calculate it.
Okay. You were just on rolls.
I got 11.4.
11.47.
Okay. Either way, okay, that's in the ballpark. I'll take it. Okay. So this displacement being positive tells us what?
Yeah, the ball is still up.
So the ball's still up.
Yeah, it's above where we started. That's what that positive displacement tells us. If our displacement came out negative, we'd be in trouble there because we threw the ball upward and it's landing below us. That's no good. Okay? So make sure you pay attention to the signs here. Okay? So we answered the first portion of our question. The second portion of our question, we can answer a couple different ways. That's the interesting thing about kinematics equations is that there's a couple different paths you could take to get to your final answer. You don't all have to solve it the same way. So I'm going to show you a couple different ways that you could solve this problem. Okay? For distance final, this is the easiest way, the best one. It only takes one equation. It works fine. Okay? The second portion where it says how long is the ball in the air until it reaches his hand, that means we want to see it go up and come back down. So it's got to go up to its peak height and back down again. Okay? So there's two ways that you can solve this. I'm going to show you one way first that I think is a little simpler, but it requires some thought. Okay, so let me show you. I'm going to get rid of this. Okay, so let's think about this here. I need you to pay attention. Here. If I'm solving, or if I'm looking at my object going up and coming back down, could I expect it to take the same amount of time to go up as it does to come back down?
No.
Why not?
Because it's different velocities.
Different air.
Different acceleration.
Nope. We ignore air resistance. Our acceleration stays the same the whole time. So these motions should be exactly symmetric, going up and coming back down. It should take the exact amount of time.
Are you serious?
I'm serious.
Even if you got Superman throwing a ball at you.
It's going to take exactly the same amount of time. Because as it reaches peak height, what does it start to do?
No.
It gets faster as it goes up? No, it goes slower. So we start with a fast speed, and here it goes slow. As it's at its peak height and it starts coming to the ground, what does it start to do? Go faster. Okay, so it's completely just opposite motions. As we throw it up, it starts fast and it slows down. As it reaches its peak height, it starts slow and it starts to increase in speed. Okay, so those two things give us exactly the same amount of time on the way up and on the way back down. Does that concept make sense? Yes or no? Everybody, I need a yes or a no from you. Okay? That concept only works for motion that is exactly symmetric. Okay, it has a line of symmetry. So this object does. It's going to start and land at the same height, which means the first half of the motion looks exactly like the second half. Okay? So this is when this shortcut method works. This is how it goes. If I know the time is equal on the way up and on the way back down, I can solve for the height I can solve for the time it takes to reach peak height, then I can multiply it by 2, right? Because it's going to be the same amount of time on the way up and the way down. So at peak height, what do I know about my final velocity?
It's 0.
It's 0. I know my initial velocity, and I know my acceleration. So I can use my easy equation, right? The first one. VF equals VI plus AT. I can use this easy equation to solve for time. Then I multiply it by 2 because this is only the time that it takes to reach peak height. Okay? This equation right here, do we see that that's the first half of the motion? Okay? I'm not giving you the shortcut to confuse you, but I think it helps. Okay? So I'm going to subtract 15 to the other side, and I get negative 9.8 times t. I'm going to divide by negative 9.8 now. My time is equal to 1.56 seconds. Is that the end of my problem? I have to multiply it by 2. Does everyone understand why I'm doing that?
Yes.
Okay, so I get 3.02, 3.12. Go ahead and plug it in. Help me out here.
I get 3.02.
Okay, depends on where you rounded this to, the time. So if I took 1.56 seconds times 2, that means I get 3.12. But if you're around that 3.0 to 3.15 range, that's fine. Okay? 3.12 seconds. The reason we multiply it again here by 2 is because this 1.56 is only the up. Okay? That means we have to multiply by 2 to make it come down. So that is one way here that we can solve for time. I'm going to show you the other way now that takes a little bit longer, but it works every time. Okay, this one works for symmetric problems, for items that look exactly the same on both paths. The next way works the same no matter what. Okay? So pay attention to how this goes now. So that was method 1. The next way that you can use to solve for time involves the quadratic formula.
Okay.
Yay. Okay, that's good. Okay? So now we're looking at the whole portion of our time. We're solving for the time that it takes to go up and come back down all at once. Okay? What do we know about the final height of this object as it reaches its hand again? As it goes up and comes back down in one trip, what's our final displacement?
0.
0, right? So if we look at the whole trip, our final displacement is 0 because it's going to start and it's going to end at the same height, which is our origin, right?
Yep.
Are we seeing that?
Yes.
Okay. So now, what equation do I have? I don't know its final velocity at its hand again, right? I don't know what this final velocity is, so I can't use that. I know my displacement final, I know my displacement initial, I know my initial velocity, and I know acceleration. And I'm solving for time. So what equation could I use? The second one, right? The second one. It looks like this. df equals di. This is a method that you will have to know because sometimes problems are not symmetric. So you will have to use the quadratic formula sometimes. So if you are just sitting back, you need to make sure you're paying attention to this. Okay, AT squared. All right, now I can plug my numbers in. My final displacement is 0 and my initial displacement is 0. That means I'm starting and I'm ending at the same height. Okay, because we're looking at the whole path of the motion here. My initial velocity was 15 times time plus 1/2 negative 9.8 times t squared. Do we see where the quadratic's coming along now?
Yeah.
0 equals 0 plus 15t plus negative 4.9t squared. So which term is my a term here? Negative 4.9 is my a term. My b term is 15, and my c term is 0. Okay, they're not in the right order, but you know the a term always goes with the squared variable, the b term always goes with the regular variable, and the c term has no variable. Okay, so let's try the quadratic formula. Anybody that doesn't remember what it is? Okay, we hear that song a lot now that you're in this chapter, okay? But let's go ahead and solve this quadratic formula. Okay, I want you to start solving it and see if we get the same time that we did using our other method. So by solving the quadratic formula, we ended up with a time equal to about 3.06, which is very close to what we got the first time. Okay, we saw this as an example when we threw the object in the air upward. Our initial velocity was positive, but our acceleration is always negative. Okay, so they don't have to be in the same direction, and that's okay. Okay, that is all right. Okay, so you don't have to write down the question that I'm asking here, but I do want you to write down the answer for the second part. So, at an object's highest point, or at its peak height, what is that object's velocity? 0. That's something that you have to remember. Okay, because it's going to seem like in problems, wow, I don't have any variables, right? They're not giving me any variables. That's because there's some hidden ones. This is one of them. Displacement initially being equal to 0 is usually one of them. Right? Acceleration equal to negative 9.8 is one of them. Those are things that they don't give you specifically in the problem that you just have to know. Yep. Okay, so that's one of them. At the object's peak height, what's its acceleration?
0. No, it's
negative 9.8.
Negative 9.8. Good. That's all the time. All the time for vertical problems, we have negative 9.8 for our acceleration. Okay? Very good.